So, if you remember the last time we discussed subtraction and said subtraction is nothing but addition of complement numbers, and in the case of binary it is 2's complement addition. A subtraction is carried out by adding 2's complement of the given number which has to be subtracted from the original number. We also found out how to get the 2's complement. It is 1's complement plus 1, and 1's complement nothing but a inversion bit by bit. That can be carried out using an exclusive OR gate, bunch of exclusive OR gates, a group of exclusive OR gates which are controlled by the subtraction bit. If you want to subtract, you pass it through them, pass it through the inverter. If it is adding, the bits do not get inverted. If you want to subtract, bits get inverted. One thing I should have mentioned earlier, actually I would like to mention now, is that we have to be very careful when we are talking of subtraction, even addition for that matter. You should be careful about the number of bits you are working with, because when you are talking of negative numbers and positive numbers, and the most significant bit being 1 for negative number and 0 for positive numbers, which bit do you look at really? For example, if I have number 3, when I ask you the binary representation of 3, you will say 1 1. Then do you think 1 is a most significant bit, and because it is 1 it is a negative? I have not told you what is the total number of bits, and in that bit you have to put all the bits in that system. You have to fill in all the positions and then look at it. Suppose I have a 4-bit number system. I have 4 bits to represent a given number, and in that if I assume the most significant bit to be a sign bit, so 1 will be represented as 0, 3 will be represented as 0 0 1 1. Since MSB is 0, number is positive, so plus 3. So that is something which I did not mention explicitly, but it is important to do that when you are doing a arithmetic operation, because our hardware is designed for a specific number of bits. You have a 4-bit adder, 8-bit adder, 4-bit multiplier, 4-bit subtractor. Arithmetic logic unit is 4-bit ALU, 8-bit ALU. So the hardware is defined for a specific number of bits, and you have to fill in all the positions before you can do the arithmetic operation. So let us assume a 4-bit number representation. And I would consider in these 4 bits, this is MSB, the sign bit, and these are the bits which represent the value of the number. So I can represent maximum of only 3 positions. In addition to that, there is a sign bit. So if 0 is positive, one is negative, so the maximum positive number is 0 1 1 1, which is plus 7. What is the maximum, minimum negative number, or maximum, whatever you want to call it, minimum, because it's a number is negative, it has a minimum value. But what is the largest number you can represent in negative? Minus 7 somebody says, minus 8 somebody says. Let us see, because this 2's complement comes into picture now. So if I put now number 1 1 1 1, because this number is 1, right, this is negative, so I will have to take the 2's complement. The 2's complement of this is 0 0 0. Of course, I need not worry about this bit anymore, because this is only a sign bit. Having taken this 2's complement of this, these are the magnitude bits. For the magnitude bits, I have to take the 2's complement. 0 0 0 plus 1 is 1. So this is one extreme. 1 1 1 1 is one extreme. The other extreme is 0 0 0 0. So 1 followed by 0 0 0, again this is a negative number. You take 1's complement, seven, right? But if we add 1 to this, so this will represent as the same number in 2's complement. 1 0 0 0, if you, this is actually minus 8, because if you put let us say 6, suppose I have 1 0 0 1, it's a negative number. What is the 2's complement of this? Add 1, so minus 7, 1 0 0 1. So 1 0 0 1 is minus 7, 0 1 1 1 is plus 7. I still have 1 0 0 0, which is a negative number because MSB is 1, but already we have reached minus 7, so I can use it to represent minus 8. So that means positive numbers go from 0 to plus 7, negative numbers goes from 0 to 8. That, so 0 positive is 0 0 0 0, 7 positive is 0 1 1 1, 7 negative would be 1 0 0 1, minus 8 would be 1 0 0 0, 1 0 0 0. It is like you start with 0 0 0, actually it is not very difficult. 0 0 0 0 0, 0 0 0 0 1 1, this is 0 1 7. What is the next number? No 8. What is this number? Minus 8. This is 8, minus 8, minus 7, minus 6. This will be what? 1 1 1 1, minus 1, because if you take the 2's complement of this, 1 1 1 will give a 0 0 0 1's complement, add 1 to it, becomes 0 0 1, so minus 1. So I have 0 to 7 and minus 8 to minus 1. The reason is I do not have to represent 0 two times. That is why I am getting one extra number for negative. I don't have plus 0 and a minus 0. I have only one 0. 0 is only once. So 0 is represented 0 0 0 0. 0 0 0 0 is 0. So 1 1 1 1 is minus 1. So if the numbers are 0 to 7 and minus 1 to minus 8, the range of numbers with 4 bits is 0 to 7 positive, minus 1 to minus 8 negative. Now in order to represent a number, I need to tell you how many bits are there and give you the sign bit clearly. That means the arithmetic operation is carried out only with the magnitude bits. Sign becomes automatically taken into account based on the addition process. So now if you want to represent two numbers, we will do two types of additions. Subtraction, of course addition is no problem. The result will always be 3 bits. So that means I have range of numbers, I can represent only 0 to 7 or minus 1 to minus 8, which means I can only represent the numbers, magnitude of these numbers using 3 bits. So all the arithmetic operations should also result, the sum or the difference should always be less than 3 bits in magnitude. Only then my this with 4-bit number with sign magnitude form a 2's complement representation, I can only carry out additions and subtractions whose result does not exceed 3 bits, whether it is positive or negative. Is that clear? Then with that background, if you look at the number, if you have 3, ask me, first thing you should ask me is this plus 3 or minus 3 we are talking about. When I say plus 3, you say 0, 0, 1, 1. So I will say 4-bit representation. I already said 4-bit representation. So 3 would be represented as 0, 0, 1, 1. Minus 3 will be represented as, I will have to take a 2's complement of this, which is 1, 1, 0, 0. Add 1 to that, becomes 1, 1, 0, 1. So in both, this is a positive number, this goes to a negative number. 1, 0, 1, 0, 1, 1. Now if you look at our addition, subtraction being the 2's complement addition, which we showed in the previous lecture, and 2's complementing can be done by passing the bits through a exclusive OR controlled by a bit which will decide whether an inversion is required or not required. Then I can draw a general 4-bit add subtract, adder subtractor using these are the numbers to be added. Oh, I have to write a little bigger than this. A's and B's. So we want A plus B, that means A plus B or A minus B we want. A plus B or A minus B. So A will be directly given. A0, A1, A2, A3. A3 being the sign bit of number A, right? Can be positive or negative. A3 is the sign bit. Similarly, B3 is the sign bit. B2, B1, B0. And this will be my add bar subtract. I will call this signal add bar subtract. What does it mean? Actually add subtract, add bar subtract, not add subtract bar. What does it mean? It is 0 if it is addition operation, 1 if it is subtraction. 0 for add operation, 1 for subtract operation. If this bit is a 1, this gets inverted. This bit is a 0, the bit does not get inverted. That is what we saw. Exclusive OR gate, the bit gets inverted if the other bit is a 1. The other bit is a 0, the bit does not get inverted. So if for subtraction we want inversion, addition we do not want inversion. So B will go through this exclusive OR gate and become plus B or minus B as required for adding or subtraction. And also the subtract signal will be used as a carry in signal. For addition, the carry in is 0. For subtraction, carry in is 1. Because with the 2's complement, we said this can only give you 1's complement. I would add one more to the 1's complement to get 2's complement. So in order to get the 2's complement, I have to add an extra 1 which is given here. Now the result would be S0, S1, S2, S3. Is carry significant or not now? Because the 4-bit adder will give you 4 some bits S0, S1, S2, S3 and a carry bit, which we will call C3. But does C3 has any use? No, because we are only talking of 3 bits now. The 4th bit is a sign bit, and our number will always be, the result will always be 3-bit magnitude and a sign bit, and the 4th S3 bit will be the sign bit, S3 will be the sign bit, S2, S1, S0 would be magnitude bits. If the sign bit is a negative number, it will be 1. If the number is negative, S3 will be 1. The result is positive, S3 will be 0. So we can now carry out addition, subtraction. A and B can take any values within 0 to 7 or -1 to -8, and the result can be only either 0 to 7 positive or -1 to -8 negative, and that will be represented by the sign bit S3. And if you want to get the original number, we don't really need it, because we wanted 2's complement representation. We given the number, we represented it and made a subtraction. 2's complement number is given to us, right? The number was complemented, a number was given to us, we complemented and subtracted it, adding extra 1. If you want to get the original number back in positive form, whether the result is positive or negative, you want the magnitude only, what I should do is to do a 2's complement one more time at the output, correct? And that can be done using the S3 bit. If the S3 bit is 1, I will again exclusive OR it. If S3 is 0, I will pass it through that. Supposing I pass this through another set of exclusive OR gates, only 3 bits, no? And this would be used to complement it if required. If the number is negative, C3 would be 1, so I can use it to complement the S0, S1, S2. Otherwise, it goes as it is. Magnitude alone. You don't need it actually, as I said. We would like to keep it in this form, because later on when we are going to go to the next computation, again you have to get the 2's complement representation of the given number. So it's good enough to have this result. But in case you want the magnitude of this number, take the 1's complement and then you have to add 1. I need one more adder. I need one more adder to this. So I will have to put this into a adder. There is nothing like a 3-bit adder. I need to have a 4th bit, the 0 input, and then 1 input. Input, oh, this is S1, S2, I'm sorry, it's not S3. This will be the magnitude of a negative number. If you had a negative number as the output, there are 2 ways of representing it. Either you can represent as it is, S3, S2, S1, S0 will give you the negative number in 2's complement form. You can keep it as it is, store it as it is, use it as it is in the next stage of addition or subtraction. That is what computers do. Computers do not keep on changing every number to sign magnitude. We are the ones who are interested in sign magnitude. We want to know the number is negative or positive and the magnitude. -17, we would rather be happy with knowing some result is -17 rather than giving this 2's complement version of it. But a computer doesn't have to. In computers, since -17 is going to be again used in next stage, what should you convert it into minus 17 and then again convert it into minus 2's complement and then use it. So most of the time this is valid. If this is the final stage and you want to display or something, positive number, negative number, so you want to again convert it back to magnitude, and somehow the sign has to be represented here. This should be the sign. So sign will be represented as minus sign, some sort of a display in which you can say this is minus because S3 is 1, and I will use this minus to invert these 3 bits to get 1's complement, add 1 to it. This is an extra circuit which is unnecessary, but if you really insist that my final result should be displayed as a sign magnitude representation, not as 2's complement representation, then you can do that. Anyway, the crux of the matter here is there is a representation of 3, whatever is the number of bits you should know beforehand. You can't just start taking a number given as it is to you, taking inverse and adding 1. Because sometimes a positive number you try to, for example, I gave you the example of 3. When I say 3, you immediately say 1, 1 and say think it is a negative number, start taking 2's complement, it is not required. If I tell you 3 using a 4-bit representation in which 4th bit is a sign bit, then you know that it is 0, 0, 1, 1. So it is a positive number, you won't do anything, you will retain 1, 1. So first question you should ask is how many bits do you have to represent my numbers, and does it include sign bit or not. If I say 4-bit including sign bit, then you know 1 bit is reserved for sign, my numbers can represent only 3 bits. And if I say further it is a 2's complement representation, I know then I can only represent 0 to 7 and minus 1 to minus 8. Okay? Then I know this is how I represent. Any number outside this range cannot be represented using this representation of 4 bits with 1 assigned bit. So if I tell you subtract 11 from 13, or if I say add 10 to 6, you will say I cannot add 10 because I don't know how to represent 10, because I can only represent 3 bits. 10 is outside my range. Or even if I say add 5 and 4, you will have to say that even though 5 and 4 are both within 3 bits representation, both are positive numbers, when I add it I will have an overflow. I have no way of handling it. If I try to add 5 and 4, it will be 9. 9 will be 1, 0, 0, 1, will be misinterpreted as negative number. 1, 0, 0, 1, you will think it is a negative number because sign bit is 1, and you will immediately start taking its complement. 1, 0, 0, 1, you will take the complement. So if I add plus 5 and plus 4, plus 5 is 4 is add. So immediately I see this negative number because I have 4-bit representation. 4th bit is a sign bit. So immediately I start taking 2's complement of this, which will be 0, 1, 1, 1, 0, and this is 7, which is wrong. But obviously this has been 9. Why is it happening? Because this exceeds the number. The number 9 exceeds the 3 bits allotted for the magnitude. 9 is 4-bit magnitude. I have allotted only 3 bits for the magnitude representation. Since it exceeds that, it's an overflow error. Of course, we will not talk about those things here. It's an overflow. It's called overflow. So first question, how many bits are there? Second question, what form is the number to be represented? So 4 bits, one of them is sign bit, then we say it's 2's complement representation, yes, then a negative number converted to 2's complement represent it. Then do an addition or subtraction, always making sure the result is less than what can be represented using the 3 bits magnitude and 1 sign bit. And further, if the result is negative, you can leave it as it is. The best way is to leave it as it is and say it's a negative number because S3 is 1. People understand it's a negative number, so the value is not that. If you want to know the actual value, you will have to take the 2's complement. But for some reason you have compulsion to display it as a sign magnitude number, you have to do one more 2's complement thing, which will involve extra hardware. So if you want, you can always look at this as a special case. S3 will be anyway there, you know. There will be 1 0 0 0. Normally look at this as the magnitude, and in the case of 1 0 0 alone, you look at S3 also. Yes. Okay, this is the subtractor adder. One other modification of this adders, we have almost completed the adders. We talked about half adders, we talked about full adders, we talked about multiple bit adder, multi-bit adders, we talked about carry propagation, we talked about carry look ahead to speed up, we talked about subtraction, we talked about complementing numbers, we talked about 2's complement and 1's complement. We said how 2's complement addition is same as subtraction. We also saw how a common hardware adder can be used for 2's complement addition as well as subtraction by taking the 2's complement of the number to be subtracted. And one variation is this is a BCD. Suppose I am talking with BCD. BCD I already mentioned this to you earlier in binary coded decimal. Suppose I have only 9, I am used to decimal number system. Because the computer or the hardware that we design deals with binary numbers, I have to necessarily convert my numbers to binary, but I am not comfortable with numbers beyond 9 because I am used to decimal representation. All the numbers I will give as decimal numbers. The computer will have a hardware which will convert my decimal into binary and do the addition, subtraction, whatever, and I would like to have my result again back in decimal representation by means of a display, 7-segment display. So that means if the result of a BCD addition, I will also like to have a BCD. That means if I have two numbers whose values are from 0 to 9, I would like to have a result which is from 0 to 18, not beyond that. Oh, so this is called BCD adder. Suppose I have two numbers, I will put A and B. You know what I mean by this arrow with a slash, means more than 1 bit, 4 bit let us say, 0 to 9. So the number can go from 0 0 0 0 to 1 0 0 1. Similarly, this can go from so what is the number now? 0 to 9, 0 to 9. I would like to have the result as 0 to 18. That's what I would like to have. But inside it is a binary adder. So when I give 9 up to 9, there is no problem. 10 will become 1 0 1 0 1 0 1 0, but I would like to have a 10 as 1 followed by a 0, 1 followed by 0. If the result is 11, let us say 8 and 3 or something, suppose this is 3 and this is 8, the result will be 11. So as far as this is concerned, it's a binary adder, it's not a BCD adder. BCD adder is only in my mind, in my concept it is a BCD, but the adder is a binary adder. This is 3, this is 8, so the result is 11. What is 11 in binary? 1 0 1 1 maybe, 1 0 1 1. So it will come as 1 0 1 1, whereas I would like to represent it as 1 followed by 1. So I would like to have a 1 followed by, I don't have to worry about 2 and all that, only 1 bit, either a 0 or a 1 here. So I would like to have a bit which is a 0 or a 1. The number is if this is a 0, 0 to 9, no problem. From 10 onwards, I will have to have a 1 followed by 0 to 8. That means whenever the number exceeds 9, I will have to do a little bit of something to bring it to what I want. Now, what can I do? to get a BCD representation of a binary sum. The maximum, when the number is 11, when the number is, let us say when the number is 9, binary, BCD, I am only talking about sum, BCD also 9, no problem. When the number is 10, I would like to have it as 1 followed by, correct, 1 followed by this 0. This is my BCD second bit, second digit. This is my second digit here, second BCD digit, 1 followed by 0, 0, 0. So from 9 it has to come to this. Okay, this would have been 10, but I want it as this 1 followed by, what is this? If you take the binary, the decimal equivalent of this number, what will be the number? 0, 0, 0, 0, 1 is equal to 16. So 1, 0, 1, 1 is 11, but I want to have this, I want to have this displayed as 1 followed by 1. Again 16, 17 this is, 1 followed by 16. So if I add beyond 9, for 10 and above, all I have to do is to add a 6 to the output. If I add a 6 to the sum beyond 9, I will get my true representation in BCD form. This I can represent separately by an LED or something, saying that when it glows it is more than 10, when it does not glow it is less than 10, I can say. So this can be a simple LED which can glow for numbers 0 to 9, not glow for numbers 0 to 9, and glow for numbers 10 to 18. So a simple LED will do, but this number I have to modify from 1010 to 0000, 1011 to 0001. That can be done by adding a 6 to that. So if you want to write the full truth table for this binary sum, BCD sum, you can complete this table yourself. I will just tell you what it is. Zero followed by, so up to 9 there is no problem. BCD sum will be same as the binary sum. Binary sum is the same as the BCD sum. The binary sum is 0 followed by 1, 1, 1, etc. up to 18 maximum. That's all. Beyond 18 we don't have to do. What is 18? 18 would be 1, 0, 0, 1, 1. This is 3 plus 15, 18. Oh, actually 19 also if you have, but 19 also can come, but it's not going to happen though. Up to 19 I have a display, because this can be 1 followed by 9. But in practice I will not have a 19 at all, because I cannot represent, each of them can only be 9, 0 to 9. When two numbers are 9, 9 plus 9 can be 18. But in practice it can be only 18, in theory it can be 19. So 19, this will be 1 followed by 9. If it is 18, 1 followed by 18, so forth. This 10 would be 1 followed by 0, 0, 0, 0. 11 will be 1 followed by 0, 0, 0, 1. 12 will be 1 followed by 0, 0, 0, 2, etc. It is this portion which has to be taken care of. This portion is no problem. I'm going to give you the circuit and later on explain how it works to save some time. You have the normal adder in which I give the two BCD numbers, 0 to 3, B0 to 3. The numbers will be anywhere from, we'll call this S0. I'll put a S0, S1, S2, S3. This is not the final sum, so I'll have to qualify this. I'll put a star here maybe. Yeah, the final sum will come later on after adding 6 to that. And then a carry. Yes?
So you need a 5-bit adder.
No, I'm going to have one more adder. Add 6. I need to add a 6 to that, right? Let me explain. Let me first draw the circuit and explain to you. So this will be added with another adder in which we'll give this. To that I have to add 6. So I need a, because this is 4 bits, this 6 has to be added, so this is a 4-bit adder. So 2 4-bit adders instead of a 5-bit adder. I am going to use 2 4-bit adders, but I cannot add always. I can only add whenever it generates a carry here. Whenever this 6 has to be added, whenever this has a, the original sum has to be first modified and then added. So this will be 2 When do you have to add 6? I have to add 6 whenever the sum exceeds 9. So how do you know the sum exceeds 9? This part of the truth table. If you study this part of the truth table, it happens whenever these two bits, binary sum, this is binary sum, S3, S2, S1, S3 bar, S3 bar, S2 bar, S1 bar, S0 bar. This is binary sum. Either this carry, which is the binary carry, this is C bar. So I have to add 6 for all these cases where C is 1, or C bar, C star is 1, or when these two are 1, this and this bits are 1, or when this and this are 1. These first two terms are taken care of by this, then all the other terms are taken care of these two, and last terms are taken care of these two. So I have to add this. We will call this the final carry, which is what is required. Final carry is the temporary carry for the binary sum, or S3 bar, S2 bar, or S3 bar, S1 bar. And this carry is also required for us. This carry will be required. The entire addition, whenever I need to carry, whenever I need to add 6 to the original sum, I have to add 6 to the sum when the number exceeds 9, when the sum exceeds 9. As soon as the sum exceeds 9, I have to have a carry addition of 6, which means I already get into my second digit. So whenever I add 6, I also should get my extra digit. This is that extra digit I was talking about, which can be 0 or 1. If it is a 0, number is less than 9, 1 if the number is greater than 10, 10 or 8. 10 to 19, this will be 1, 0 to 9 will be 0. That is what I meant by putting a simple LED to show this number is less than 9 or greater than 9. When do we add 6? Whenever the number exceeds 9. How do you know when the number exceeds 9? By looking at this. So this is the combination. Whenever number exceeds 9, we are going to have this combination of either the last bit is 1, a carry bit is 1, that is the last 16, 17, 18, 19. Up to 15, this will be 0. This is 16, 17, 18, 19. Last 4 rows of my truth table, I want you to complete the truth table as an exercise, because this truth table will have 9 here, another 9 here. Now 10 to 19, 10 entries, 0 to 9, 10 entries, another 10 entries. In this last 4 rows of this, here will be, anyway you have to add 6, or when this and this, which is the last 2 bits of the sum, original sum, are 1, we need to add 6, or when the first S3 and S1, this and this are both 1. So this, if you write the full truth table, you will find that the pattern will emerge. Whenever there is a 1 here, or whenever there is a 1 here and here, or whenever there is a 1 here and here, these are the 3 conditions at which I add 6. So that is what is represented here. If the original carry, original addition results in a carry, which is for number greater than 15, this C star takes care of 16, 17, 18, 19, because 4 bits can only represent 0 to 15. But number can be anywhere from 0 to 19 theoretically, practically 0 to 18. So I need to have 4 conditions, 4 possibilities of number being 16, 17, 18, 19. That is taken care of by this. Or whenever the number is greater than 9. How do you represent number greater than 4 bits? Number greater than 1010, start from 1010 right up to 1111. You will find that in this case I cannot put 1 here directly, because this one also will be here. So when this is 1 and this is 1, or when this is 1 and this is 1, these 2 conditions also taken care of, number 9, number exceeding 9. So this is the condition for which I need to add 6. So 6 is nothing but 0, 1, 1, 0. 0, 1, 1, 0. The 0 I will put permanently, this 1 I will take whenever this output is there. So this is the, this OR gate implements this function. This Boolean function implements this OR gate. So whenever this OR gate has an output 1, we will have 1 added, at the same time we will have this as the carry. So the 18th number, S0, S1, S2, S3 plus carry, the BCD addition will come out of this. 6 has to be added, no problem. I have to take the binary addition, I need to take another binary adder, 4-bit adder, add 6. But it is not that simple. I can only add 6 under certain circumstances. What are the circumstances under which I have to add this 6? Depends on whether there is a carry in the original addition, or whenever the number exceeds 10. So whenever the number exceeds 10, so this represent, these 2 terms represent the condition under which number exceeds 10, number is 10 to 15. Number is 10 to 15, these 2 terms. This term exceeds 16. 16, 17, 18, 19 are taken by this, taken care of by this term. These 2 terms take care of the fact that number is between 10 to 15, 10, 11, 12, 13, 15. So once these 3, one of these 3 conditions are met, I need to add 1, 1, 0, 1, 1, 1, 0. 0, 1, 1, 0 is 6. Original number plus 6 gives you. Otherwise, this will be 0, this BC number from 0 to 9, if the result is 0 to 9, this C will be 0, so I will be adding 0, 0, 0, 0, so that means original number will come out as the correct final number, and this also will be 0. This is BCD addition. This is what happens really, because I need to have a BCD representation only for display purpose again. If you are using this as an intermediate result for the next processing, you can treat with binary numbers, all binary numbers. But if you are taking digital numbers, decimal numbers, and treating them digit by digit, I want to have a calculator, for example. I need to punch in decimal digit, I want a result decimal. Inside that may be binary, but I want decimal input, decimal output. So this is what happens in a calculator. If the number exceeds, supposing you try to make a simple calculation of 5 and 7, excuse me, number to be 12. When 12 will be, if 5 will be converted as 0, 1, 0, 1, 7 will be converted as 0, 1, 1, 1, result will be 1, 1, 0, 0. No problem. But I want the result to be displayed as not 0, 1, 1, 1, 1, 0, 0. I want the result to be displayed as 1, 2. That means I need to add 6 to that. It becomes 18. Out of that 18, that 1 will come separately. 16, that last one is the 16 number. If you remove that 16, the remaining is 2. The 2 will be converted as 2, and it will blow the 7-segment display. So 16, what is that I said? 18, 12, 5 and 7, no problem. 12, but I don't want this, so I add 6 to that. This one will come as 1 by where 7-segment display. These 2 will come as 7-segment display. That is why you are able to see 12 in your calculator, not 1, 1, 0, 0. This is exactly the point. So I should know, I should add 6 because this is more than 9. 10 and above I need to add 6. That's what I did. Okay.